Greetings. Today, we delve into a world where tiny quartz crystals, mass-produced in secret American factories, would prove to be the ultimate game-changer in wartime technology. A single captured radio in Tunisia reveals that, against decades of German propaganda, the Americans had developed a revolutionary, mass-produced communication system, featuring crystal-controlled oscillators, automatic frequency control, and modular design, that outpaced German engineering by years, if not decades. How could a simple component like a quartz crystal embody such a technological leap? What secrets did these radios hide about America's industrial might? And crucially, what does this say about the true battleground of modern warfare? The answers lie in the astonishing scale of American manufacturing, producing millions of high-precision crystals, advanced FM radios, and reliable, easy-to-operate systems, while Germany could only dream of matching such industrial capacity. Because, in a war of factories, the key to victory was no longer just skill on the battlefield but the relentless power to produce the future's weaponry at an unparalleled scale. The most critical question now is, how did this tiny crystal, crafted with extraordinary precision, symbolize a fundamental shift, from tactics and heroism to the raw force of industrial strength, that would define military success in the decades to come? The answer begins right now. On the 16th of February in the year 1943, a subtle tremor coursed through the hand of Oberg engineer Klaus Hermann as he carefully unlocked the sealed metallic container that housed the American radio set they had just captured. Surrounding him, 5 of Germany's most skilled and experienced radio engineers leaned in with intense anticipation, all eager to scrutinize the technological marvel that had fallen into their possession during a recent engagement at Kasserine Pass. For 3 long years, German authorities and military officials had been fed a consistent narrative from bunker to bureau, asserting that American technology was fundamentally inferior. They dismissed American engineering as nothing more than crude, mass-produced junk, crafted by a nation of shopkeepers and assembly line operators lacking true sophistication. The intelligence reports from the WWII's radio service echoed this sentiment, claiming that American forces relied on antiquated equipment, primitive designs, and poorly trained personnel, an assumption meant to foster confidence in the German military's technological superiority. But the scene before them now told a different story altogether. Despite their propaganda, German military intelligence was observing undeniable signs of sophisticated, tightly integrated communications. Allied forces were maintaining unbroken lines of contact across immense distances, their ships communicating at ranges that defied the supposed technological limitations. Ground units executed maneuvers with an uncanny precision, their coordination suggesting the use of advanced radio systems far beyond the simple radios their enemies purportedly used. The sealed case was gradually opened to reveal an 508 Seychelles rupees radio set, which had been captured directly from an American M4 Sherman tank that had been destroyed amidst the rugged mountains of Tunisia. What Klaus Hermann and his team uncovered over the subsequent 72 hours would fundamentally alter their understanding of the American capacity for technological innovation, industrial production, and strategic planning. It was a discovery that would shatter every previous assumption held about American military prowess. By examining the mathematics behind radio communications, they were on the brink of uncovering a truth far more devastating than any battlefield loss. Their intensive analysis would unveil not merely a technological disparity but an expansive industrial gap, an abyss so profound that the very fabric of Germany's war effort could be seen reflected in the intricacies of frequency crystals, automatic circuits, and mass manufacturing techniques. These were elements Germany's industries would never be able to replicate swiftly or effectively. The process of capturing this crucial technology had begun on February 14, when the German forces at Kasserine Pass launched a counterattack to halt the advancing inexperienced American troops. Their effort resulted in a tactical victory, forcing the United States Second Corps back by approximately 50 miles and destroying over 100 American tanks during the clash. In the aftermath, German technical intelligence teams moved swiftly among the wrecks, scouring the battlefield for weapons, documents, and equipment that could yield insights into Allied technological capabilities and operational methods. Among these teams was Headman Friedrich Weber, a seasoned officer commanding a signals intelligence detachment attached to the 21st Panzer Division. His orders were explicit: to locate and secure any American radio equipment intact, an opportunity that could shed invaluable light on the enemy's communications strategy. In a crater situated east of Kasserine Pass, his team chanced upon an abandoned Sherman tank. The turret had been shattered, blown off by a German 88mm artillery round, but remarkably, the tank's radio compartment remained undamaged and intact. Within this compartment, Weber's team discovered not one but two complete radios: the 508 Seychelles Rupees model, designed specifically for tank-to-tank communication, and an 510 Seychelles Rupees receiver. Both sets were remarkably preserved, with their crystals, connecting cables, and even the technical manuals still secured in their original mounting brackets. Recognizing the significance of this find, Weber ordered that both pieces of equipment be transported without delay to the nearest German technical testing station, an essential move to achieve a comprehensive understanding of their operational capabilities. By the morning of February 16, the radios had arrived at Technical Testing Station 12, where detailed examinations and analyses could begin to piece together the complex mechanics hidden within. Hidden deep within an underground complex beneath the city of Tunis, there was a secret facility that housed some of the most advanced radio engineering talent in the world. This was no ordinary workshop. It was a highly specialized laboratory operated by the Germans, staffed with top-tier radio engineers who had previously designed and perfected the communication systems used by the Wehrmacht itself. Among these specialists was Oberingenieur Klaus Hermann, a veteran chief designer from the firm Telefunken, who led the team assigned to scrutinize these foreign communications devices. Accompanying him were a cadre of experts in various critical fields, including frequency generation, circuit design, manufacturing techniques, and signals intelligence, all brought together to analyze and understand the technological marvels they had uncovered. Their initial step was an external inspection of the radio units. These American radios were encased in sturdy steel housings, painted in the characteristic olive drab color, designed for durability in combat conditions. Rubber gaskets surrounded every seam and connector, ensuring that water, dust, shock, and temperature extremes, conditions that would swiftly incapacitate typical German radios, were effectively resisted. Hermann noted in his first report that the build quality exceeded anything he had encountered in German military equipment, marking a striking difference in manufacturing standards. However, it was only when they removed the protective steel cases that the full extent of the ingenuity became apparent. Inside, the design revealed a standardized, modular architecture, an approach that emphasized mass production and ease of assembly. Every component inside was manufactured to identical specifications, precisely documented in accompanying technical manuals. There were no hand-tuned adjustments, no technician marks indicating individualized calibration, and no parts that suggested skilled, artisanal craftsmanship. Instead, the equipment was created with the intent of being assembled automatically by semi-skilled workers in factories spread across a continent, enabling rapid, large-scale production. One of the key figures examining the internal components was Leighton Hans Schreiber, a specialist in frequency control. He focused on the crystal units responsible for setting the radio's operating frequencies. Expecting to find simple and inexpensive crystals, perhaps even salvaged civilian components, he was taken aback. Instead, what lay before him were highly precise quartz crystal oscillators, each meticulously ground to tolerances measured in parts per million. These crystals were hermetically sealed within metallic holders, manufactured to specifications that would have taken weeks of laboratory work in Germany to produce. The SC County Route 508 model, in particular, was fitted with 10 crystal-controlled channels. Each crystal was individually packaged, interchangeable, marked with precise frequency specifications, and neatly installed within the radio housing. Schreiber, overwhelmed by the sight, counted the crystals twice to confirm his observations. It was difficult to grasp the scope of what he was witnessing. In Germany, crystal-controlled radios were luxury reserved for high-command units and aircraft, where the scarcity and expense of these ultra-precise crystals justified their use. Yet, here they were, installed in a standard American tank radio, 10 crystals per unit, in a manner as casual and commonplace as installing a light bulb. Carefully, Schreiber removed one of these crystals for closer examination under a magnifying lens. The quartz crystal was flawless, the electrodes aligned with absolute precision, and the frequency marked on its surface was exact. This tiny component, so small that it seemed almost insignificant, represented a level of craftsmanship and technical sophistication that could easily have cost more than the entire German FUG-5 radio set in terms of materials and labor. The Americans, however, did not consider these crystals a luxury. They had already produced thousands of Sherman tanks, each equipped with multiple crystal-controlled radios working on different channels. The initial analysis uncovered even more startling facts. The radio operated not on the traditional amplitude modulation, AM, that the Germans relied on but instead utilized frequency modulation, FM. In theory, FM should have provided superior communication quality, delivering static-free signals and greater resistance to interference. Yet, employing FM demanded far more complex circuits and exacting frequency control, presenting a formidable challenge for standard manufacturing. This discovery was startling because it indicated a significant technological leap. The Germans' communication systems had traditionally depended on AM, which was simpler to implement but more susceptible to static and jamming. The shift to FM, which was considered revolutionary at the time, suggested a deliberate attempt by the Americans to outpace their opponents with superior technological means. It hinted at collaborative advancements in circuit design, miniaturization, and precision manufacturing that could potentially tilt the balance of battlefield communications in favor of the Allies. In sum, the examination revealed a sophisticated, mass-produced radio system far beyond ordinary military standards. The quality and complexity of the components, especially the crystal oscillators, demonstrated a level of technological innovation that was both impressive and somewhat alarming. It underscored how, amidst the chaos of war, the Americans had managed to develop and deploy cutting-edge communications gear that could operate flawlessly under adverse conditions, and which embodied the pinnacle of available technological progress at that time. Despite initial reservations, the Germans had long considered the potential of frequency modulation, or FM, for military communications. However, they ultimately dismissed it as too costly and too complex to implement effectively in the field. Their reasoning was rooted in the substantial demands FM technology placed on equipment, requiring intricate circuitry and precise manufacturing. Yet, Here was an unexpected surprise. An FM radio, mass-produced on a scale that suggested it was intended for regular military deployment, was now in their hands. It was installed within a tank that young American soldiers were operating, a fact that emphasized its significance. Examining the circuit board, the German engineers noticed something remarkable: advanced automatic frequency control, known as AFC, circuits. These systems allowed the radio to automatically lock onto a specific frequency, maintaining stable communication without the need for constant manual adjustments. In stark contrast, the German radios they were familiar with demanded persistent operator intervention. Those earlier systems relied heavily on operators to finely tune the receiver to compensate for changes caused by temperature fluctuations, aging components, and variations in power supply. Such manual tuning was tedious and prone to errors, especially under the stressful conditions of combat. In comparison, the American radios seemed to possess a self-tuning capability that was astonishing for the time. Oberleutnant Hermann, one of the senior engineers, began drafting a detailed report for the High Command of the Wehrmacht stationed back in Berlin. His words flowed cautiously at first, but with growing conviction, as he recognized the implications of his findings. Each sentence seemed to challenge and even contradict Soviet and German intelligence assessments, which had long underestimated American technological advancements. Hermann noted that the captured radio represented a new frontier in industrial manufacturing, an echelon of sophistication that Germany, with its existing infrastructure, could not hope to emulate. The components strutted a level of precision that demanded highly specialized factories, carefully trained technicians, and rigorous quality control processes, elements that were severely lacking within the Reich's industrial base. More alarmingly, the design of this radio was clearly not a prototype or limited-run experimental device. It bore the unmistakable characteristics of a mass-produced weapon of communication. Every aspect of its construction betrayed a philosophy of high-volume manufacture. Clearly, the Americans were producing these radios in the thousands, if not tens of thousands. Over the course of the next 3 days, the German team methodically tested every function of these captured units. They connected the radios to various power supplies, tested their antenna systems, and employed an array of test instruments inside the underground laboratory, an environment carefully chosen to minimize interference. Each test raised more concerns, and with every new discovery, their unease grew. The 508 Seychelles rupees model's transmitter was capable of producing a clean, high-quality FM signal, delivering 25 watts of power on any of 10 selectable channels. The switching mechanism behind this selection process was elegant and highly reliable, an example of thoughtful engineering. It required no special training to operate. A tank commander only had to rotate a knob to select a preset crystal frequency. The radio then automatically switched channels, retuned its internal circuits, and sustained a perfect transmission quality, all without manual intervention. When comparing this to German communications equipment, the differences were stark. German radios necessitated a trained operator for every frequency change. The operator had to manually adjust multiple dials, swap out coils, and spend several minutes retuning the entire apparatus, an effort both time-consuming and vulnerable to error. The Americans, by contrast, had created a system that was simple, fast, and dependable, properties crucial for battlefield communications. Range tests were equally troubling. Using a captured American whip antenna, the Germans managed to establish contact with a monitoring station located 20 kilometers away. To their amazement, the FM signal arrived clearly, free of the static and fading interference that marred their own amplitude modulation, or AM, signals. Even when deliberately introducing electrical noise, such as from a tank engine, the FM receiver's limiter circuits proved remarkably effective at filtering out interference. The audio transmitted through these units was consistently clean, offering clarity that German operators could only dream of achieving with their traditional systems. Lieutenant Schreiber, a meticulous engineer, escalated his scrutiny, focusing his attention on the crystal oscillator circuits, the heart of the radio's frequency stability. He meticulously traced every component, measuring voltages with precision and documenting the entire circuit design in painstaking detail. What he uncovered confirmed the worst fears of the German team. The crystal control system involved a level of sophistication that went far beyond their manufacturing capabilities. The construction of each crystal oscillator required not only exacting design but also the use of highly specialized processes. In particular, each crystal was made from a quartz plate, which needed to be ground to an extraordinarily precise shape and size, an operation demanding finely calibrated cutting and polishing techniques. The process necessitated equipment and trained personnel that simply did not exist within the German industrial infrastructure. These crystal oscillators provided a frequency stability and accuracy that was all but unachievable in German-made devices, further underscoring the technological disparity between the two nations' war efforts. The manufacturing process involved extremely precise measurements, often expressed in thousandths of a millimeter. Once crafted, these delicate crystals were carefully mounted within evacuated or gas-filled holders, where the spacing between electrodes was controlled to tolerances that German factories could hardly replicate on a large scale. To ensure stability across a broad temperature range, from as low as 40 degrees below zero to as high as 60 degrees above, temperature compensation circuits were meticulously integrated into the design. These circuits played a crucial role in maintaining the frequency stability of each crystal, essential for reliable radio operation. In his detailed calculations, Schreiber estimated that producing a single crystal to American standards would demand around 40 hours of highly skilled technician labor at German laboratories. Yet, in stark contrast, the Americans had managed to place 10 such precision crystals into a single tank radio, demonstrating their impressive manufacturing capabilities. Considering that thousands of Sherman tanks were already in active service, along with similarly equipped radios in American jeeps, trucks, and commanding vehicles, it was clear that the United States was producing millions of these high-precision radio crystals every year. This raises an obvious and pressing question. Where did the Americans find enough trained technicians to handle this vast volume of highly precise component manufacturing? The answer, when obtained from well-informed sources, was even more startling. The United States was not relying heavily on highly trained individual technicians for production. Instead, they had succeeded in industrializing and automating the entire process. New facilities established in cities like Chicago, Newark, and Fort Wayne employed thousands of semi-skilled workers, predominantly women, who operated specialized grinding machines designed for automatic crystal production. Instead of individual artisans painstakingly crafting each crystal, the Americans used optical comparators and electronic frequency counters to perform quality checks, replacing the need for skilled technicians with automated, high-speed measurement systems. Statistical process control became the norm, with random samples from production batches subjected to testing rather than examining every single crystal. This transformation turned what was once a highly specialized laboratory craft into a streamlined, large-scale industrial operation. Further examination of the receiver components revealed even more remarkable technological advancements. The superheterodyne circuit design closely resembled German models, yet the American versions featured components of superior quality. Vacuum tubes were manufactured to tighter tolerances, with characteristics that perfectly matched the specific needs of the circuits they served. Capacitors and resistors exhibited stability ratings far exceeding what German-made parts could offer, ensuring consistent performance under various operational conditions. The entire receiver architecture was purposefully designed for ease of alignment, requiring only semi-skilled technicians armed with simple testing equipment, rather than highly trained radio engineers, to perform setup and maintenance. Perhaps most revolutionary was the modular construction approach. Every major subsystem, be it the transmitter, receiver, power supply, or control units, was built as a separate, easily replaceable module. If a component failed, a crew could quickly remove the defective module and swap in a new one within minutes, often without the need for tools or technical expertise. Damaged or faulty modules would then be sent back to depot facilities for repair or disposal. This modular design demanded enormous industrial capacity to produce a steady supply of spare modules but offered a significant tactical advantage. Tanks equipped with such systems could restore their communications rapidly in the field, even under battle conditions that might leave German vehicles silent for days while technicians performed extensive repairs. The accompanying technical manuals further underscored this practical, user-friendly approach. Printed on high-quality paper with clear diagrams and straightforward instructions, these manuals assumed minimal technical knowledge on the part of the operators. This streamlined training requirement meant that even crew members with only basic technical understanding could operate, troubleshoot, and replace modules efficiently, ensuring that radio functionality was maintained under the most challenging battlefield conditions. Rosses revealed further gaps in German understanding and capabilities, underscoring just how far American technological advancements had advanced beyond their own. Sherman and his team knew that the enormous disparities in design philosophy and industrial capacity could not be bridged quickly or easily. The American approach to radio technology emphasized simplicity, reliability, and ease of operation, aligning with their broader military doctrine that prioritized mass production and usability over intricate technical mastery. Instead of expecting every soldier to become an electronics expert, they engineered equipment that could be operated effectively following straightforward, step-by-step procedures. Manuals that broke down complex troubleshootings into clear decision trees, much like flowcharts a soldier could follow without specialized training. In these manuals, troubleshooting schemes were laid out systematically, allowing even an untrained infantryman to identify faults, locate defective components, and perform basic repairs. Instead of relying on operator intuition or specialized knowledge, maintenance routines specified precise intervals for replacing parts, such as tubes, resistors, or crystals, eliminating guesswork and extending the operational lifespan of the equipment. This strategic shift meant that maintenance was standardized, predictable, and far less dependent on skilled technicians, which dramatically improved battlefield communication resilience. Sherman recognized that these manuals reflected a deep-rooted American military engineering philosophy, one that accepted a fundamental truth: frontline soldiers were not electronics specialists. By designing radio systems that demanded minimal technical expertise to operate and repair, the Americans effectively democratized maintenance, significantly reducing the dependence on skilled personnel and making their communications networks more robust under combat conditions. In contrast, German radios required highly trained specialists who understood the complexities of radio theory, could conduct field repairs, and possessed the technical judgment necessary to address unpredictable malfunctions. Such operators underwent months, sometimes even years, of intensive training before they could operate and repair these sophisticated devices. These individuals became invaluable assets, and the loss or injury of such a technician often rendered the equipment they managed completely useless to whomever inherited their responsibilities. By the end of the third day of testing, the German team had meticulously examined every aspect of the captured American radios. They documented each circuit, measured all components, and rigorously tested every function, compiling an exhaustive technical report. This detailed analysis, which spanned over 200 pages and included photographs, circuit diagrams, and detailed specifications of every component, delivered a crushing blow to German confidence. The report presented a sobering conclusion. American radio technology was not just competitive but decisively ahead in key areas, by anywhere from 5 to 10 years' worth of development. Critical innovations such as frequency modulation, crystal-controlled oscillators, automatic frequency circuits, and modular construction had established a technological edge that could not be offset merely through superior tactics, training, or operator expertise. Furthermore, American radio equipment was fundamentally designed with mass production in mind. Every element of its construction echoed an industrial mindset centered on standardized manufacturing processes, interchangeable parts, and rapid assembly lines, concepts that Germany lacked or had not adapted fully. This industrial philosophy allowed the American military to produce vast quantities of reliable, high-performance radios quickly and efficiently, a capability that no German facility could match without substantial reorganization. Estimations provided in Herman's report laid bare the enormity of the challenge facing the German war effort. To achieve parity in radio production, Germany would need to establish approximately 30 new specialized factories, train an additional 50,000 workers, and allocate resources roughly equivalent to their entire annual Luftwaffe budget. Even under these strained conditions, the report highlighted severe shortages of critical raw materials, particularly high-quality quartz crystals and special rare earth elements used in precision components. The overarching conclusion was stark. American industrial capacity, coupled with their technological innovations, had rendered German forces significantly disadvantaged in communications technology. This superiority was a decisive factor that would influence the course of the war, making tactical and operational advantages increasingly vulnerable to technological inferiority. The report was received in Berlin on February 25, 1943, and was immediately classified as most secret. Only a select few senior officers within the Wehrmacht High Command and the Reich Ministry of Armaments received copies. Yet, despite the gravity of its findings, the response was marked by quiet denial. No new factories were authorized, and no large-scale efforts for rapid production were initiated. The implications of the report were too painful or too politically delicate to confront openly. Acknowledging this technological gap meant admitting a looming strategic vulnerability that no quick fix could remedy. Nevertheless, the work of the German Technical Testing Station, No. 12, was only beginning. Over the following months, additional American equipment continued to fall into German hands, each new capture further exposing the depth of their technological gap. Every new piece of hardware scrutinized, every circuit analyzed, reaffirmed Herman's and his colleagues' grim understanding. The American lead in radio technology was not a temporary advantage but a fundamental shift that Germany would struggle to overcome in the foreseeable future. The discovery of new evidence highlighted the remarkable superiority of American military technology and industrial capability during World War II. Among the most impressive pieces of equipment was the -300 Seychelles rupees, famously known as the backpack walkie-talkie. This innovative device incorporated FM technology, which was a significant advancement at the time, and it had been miniaturized into a truly portable unit weighing only about 18 pounds. Despite its lightweight construction, the SCR300 could provide dependable communication links over distances reaching up to 5 kilometers, a feat that was highly valued in the field. In stark contrast, similar portable radios used by German forces of comparable range were considerably heavier, often exceeding 40 pounds in weight, and required the use of external battery packs that added an extra 20 pounds to their overall mass. The disparity in design and functionality became even more apparent when examining a remarkable piece of German equipment known as the SCR299, which was captured by Allied forces during their campaign in Sicily in July of the year 1943. This device represented a significant leap forward, being a mobile, long-range communications station installed within a truck that housed an integrated power generator. Its transmitter was capable of producing 350 watts of power, functioning reliably over a frequency spectrum from 2 to 18 MHz. Thanks to crystal-controlled stability, the SCR299 could swiftly change frequencies, shifting from one channel to another in a matter of minutes rather than hours, a feature that greatly enhanced battlefield flexibility. The accompanying receiver was built around a Helic-Rodini design, equipped with 15 vacuum tubes, multiple conversion stages, and a crystal filter, which collectively contributed to improved selectivity and clarity in reception. While German forces did possess long-range communication systems of similar capabilities, these were predominantly fixed installations requiring large-scale antenna structures and dedicated power plants, complex setups that could scarcely be moved and required substantial infrastructure. Conversely, the Americans had managed to pack comparable capabilities into a mobile package, mounted on a vehicle capable of being driven anywhere and set up within roughly an hour. This pattern of technological advantage was consistently observed across different examples. The underlying philosophy behind American electronic equipment was also markedly different from that of their German counterparts. American devices were engineered for ease of use by personnel with minimal training, enabling mass production by semi-skilled workers and straightforward maintenance procedures. This approach prioritized simplicity, affordability, and deployability. On the other hand, German radio systems demanded highly skilled operators, hand assembly by trained technicians, and field repairs carried out by electronics experts, requirements that limited their rapid deployment and widespread usage. This divergence in design philosophy reflected a strategic difference. The American approach scaled efficiently to support millions of units and global deployment, whereas the German approach, although technologically capable, was more suited to fixed, specialized installations. The technical intelligence gathered from various campaigns in Tunisia, Sicily, and later Italy painted a clear picture, not merely of individual radio sets, but of an overarching communications strategy. American forces maintained a continuous flow of information, establishing layered radio networks that linked squads to theater command. For instance, platoons equipped with -536 Seychelles rupees handheld transceivers could maintain contact with their company units armed with -300 Seychelles rupees backpack radios. These company-level units communicated with battalion-level vehicles carrying -508 Seychelles rupees and -608 Seychelles rupees long-range sets, which in turn linked to regimental stations like -193 Seychelles rupees and -299 Seychelles rupees. This interconnected system created a resilient web of communication, ensuring that orders, intelligence, and reports could be rapidly relayed across all levels, something the Germans found difficult to match. More importantly, All American radio systems employed compatible frequency ranges and interoperable equipment, fostering seamless coordination. For example, a forward observer wielding an -300 Seychelles rupees could contact an artillery battalion 20 kilometers away using an SCR508, because both units operated on FM frequencies controlled by crystal stabilization, ensuring reliable communication even at extensive distances. In comparison, German forces operated multiple incompatible systems, each with different frequency requirements, modulation methods, and operational procedures, which hindered their ability to form a cohesive communication network. By mid-1943, German signals intelligence had documented over 50 different American military radio types, ranging from small handheld transceivers to larger airborne command sets. Intelligence reports and captured serial numbers indicated that American factories were producing in excess of 100,000 military radio units each month, a staggering output that underscored the industrial scale behind the Allied communication advantage. The sheer volume and diversity of American radio equipment allowed for a flexible and robust command and control structure that German forces could not readily imitate or counter. At the height of their production capabilities, the American electronic manufacturing sector was capable of producing approximately 15,000 units each month, a figure that reflects the immense scale and efficiency of their mass production systems. As the war progressed, European intelligence units, especially the Germans, began to scrutinize and analyze the wealth of documentation captured from American factories, uncovering insights into how these advanced industrial systems operated behind the scenes. Examining the technical orders, parts lists, and maintenance manuals provided a window into the sophisticated infrastructure that underpinned American manufacturing processes. A striking revelation was the remarkable standardization embedded across a wide array of radio equipment. Components such as vacuum tubes were designed with universal base configurations, allowing for universal compatibility and interchangeability. Crystals, for instance, adhered to standard holder designs, simplifying both manufacturing and repairs. Even the smaller hardware elements like screws, nuts, and bolts followed unified threading standards, which facilitated easy replacement and interchange between different units. This comprehensive standardization was a fundamental aspect of American manufacturing philosophy, enabling factories to undertake flexible production shifts between various radio models with minimal retooling. For example, a plant dedicated to producing 508 Seychelles rupees transmitters could transition seamlessly to 608 Seychelles rupees units by simply swapping out a few fixtures and adjusting a handful of components. The practice of salvaging parts from one radio type to repair others further exemplified a strategic emphasis on resource efficiency and versatility. The overall system was engineered for both scalability and adaptability, allowing a rapid response to evolving military demands. In stark contrast, German manufacturing practices relied heavily on custom-designed components tailored specifically to each piece of equipment. The German FUG-5 tank radio, for example, shared virtually no parts with the FUG-10 aircraft radio, despite performing similar electrical functions. Each type of radio required its own dedicated production lines, specialized testing apparatus, and a unique inventory of spare parts. Such bespoke manufacturing approaches meant that any shift in production priorities was a lengthy process, often requiring months of retooling and retraining personnel to adapt to new component requirements. By the autumn of 1943, the engineer Hermann from the Oberkommando der Wehrmacht, OB, who had been working in Italy, had shifted his focus from purely technical analysis to broader intelligence assessments. His reports to Berlin gradually transitioned from detailed evaluations of radio circuit designs to urgent strategic warnings about the burgeoning industrial capacity of the Americans. Sherman meticulously documented the rapid growth of the American electronics industry, revealing its exponential expansion and the technological advances driving it. American companies such as Galvin Manufacturing, later known as Motorola, had evolved from modest radio producers into colossal military contractors within a matter of years. Helicrafters, a well-known manufacturer of amateur radio equipment, had begun producing highly sophisticated military receivers in quantities that remarkably exceeded the total German radio production efforts. Western Electric, the manufacturing arm of the renowned Bell telephone system, operated sprawling factories employing tens of thousands of workers who produced a vast array of components, including crystals, vacuum tubes, and complete radio sets. Notably, these companies had scarcely existed as major players prior to 1941, but within less than 2 years, they had transformed into a fully integrated military electronics industry. They achieved this rapid evolution by converting existing civilian factories, leveraging the skills of newly trained workers, and applying mass production techniques that had been perfected within the automotive and consumer appliance industries. Detroit's automotive engineers, for example, adapted their highly efficient assembly line expertise to radio production, implementing streamlined processes that rivaled automobile manufacturing in speed and scale. Meanwhile, on the German side, the radio industry remained rooted in the organizational structure and production methods of the 1920s. The industry was concentrated in major cities such as Berlin, Munich, and Hamburg, where small manufacturers continued to produce specialized equipment using highly skilled craftsmen. Production volumes remained relatively modest, measured in hundreds of units per month rather than thousands per week. Quality control was primarily upheld through painstaking individual inspections and manual adjustments, eschewing the statistical quality assurance methods that characterized American mass production. Thus, while American industry rapidly scaled and standardized its manufacturing processes, German radio production remained largely artisanal and segmented, reflecting a fundamental divergence in industrial strategy and capacity during the war years. The landscape of process control and automation in the realm of military technology during the early 1940s reveals a stark contrast between American and German industrial capabilities. This disparity became crystal clear through detailed analyses, such as Sherman's report from December of 1943, addressed to the Reich Ministry of Armaments. The document, titled The American Radio Industry, An Assessment of Industrial Capacity and Strategic Implications, meticulously catalogued the sprawling scale and sophistication of American electronics production. According to Sherman's findings, the United States was manufacturing annually an amount of electronic equipment that would have taken Germany 2 decades to produce under its own industrial conditions. This was not merely a technological advantage but a profound structural gap encompassing industrial scale, organizational efficiency, and philosophical approach towards manufacturing and innovation. The report estimated that American factories possessed enough capacity to produce radio equipment sufficient to outfit 1,000 divisions, an astonishing figure considering the Germans fielded only about 90 divisions at that point in the war. Such excess capacity meant that American military forces had an almost unlimited supply of replacement radios. In contrast to German tactics, where damaged radios in the field were painstakingly repaired by technicians often under dangerous combat conditions, American units simply threw out the broken equipment and replaced it with fresh units from mass production. Outdated models did not linger; instead, they were phased out entirely and sent to training camps for instructional purposes. Every new model introduced into the American military was not a prototype but a fully mass-produced design, rapidly distributed across entire theaters of operation. Meanwhile, on the German side, every radio piece was a precious resource. German forces meticulously conserved every unit, undertaking repairs in the field that often involved cannibalizing functioning radios to replace broken parts. Replacement radios were delivered sporadically, if at all, which further complicated operational mechanics. The introduction of newer designs was limited, as retooling factories to produce modernized equipment would have dramatically reduced the output of existing models. This resulted in a fragmented technology landscape. German units used radios designed in the early 1930s alongside newer models, creating operational chaos for maintenance crews and complicating training programs. The critical supply of quartz crystals posed one of the most severe bottlenecks in German radio manufacturing. By late 1943, German quartermasters calculated that they needed approximately 5 million precision crystals to maintain current equipment and to implement planned upgrades. Yet, domestic production capacity was around 200,000 crystals per year. Even with enormous resource investment, it would have taken more than a decade to produce the required number of crystals. Meanwhile, intelligence estimates revealed that American crystal production exceeded 30 million annually, thanks to discoveries of deposits in Brazil, extensive mining in Arkansas, and even pioneering synthetic crystal manufacturing experiments. American crystals, in addition to their abundance, were of superior quality, demonstrating frequency stability that German laboratories could scarcely measure, let alone reproduce. A further revealing aspect of the industrial gap lay in the inspection and testing of radio equipment. When examining captured American test devices, it became obvious that America's manufacturing process was highly advanced. American factories employed automated testing sets capable of measuring frequency, power output, modulation quality, and sensitivity in mere seconds. These sophisticated electronic instruments were produced in such large quantities that each station on an assembly line could have its dedicated test equipment, ensuring quality control at every step. In stark contrast, German factories relied on manual procedures for testing, requiring skilled technicians to perform measurements, often taking several minutes per unit. One particular item captured by German forces was a signal generator from a measurements corporation, an American-designed test set that was considered highly valuable in the technical testing facility. This single instrument illustrated the technological edge held by the Americans. It could generate precise signals quickly, streamlining the process of testing and ensuring high standards of performance. The disparity between American and German standards extended beyond simple manufacturing techniques to the fundamental approach to quality control and automation. American production lines, equipped with automated testing and relentless quality assurance, dramatically accelerated the pace of production and maintained high levels of reliability. German efforts, hamstrung by manual processes and limited technological resources, struggled to keep up, facing constant shortages and operational difficulties. In sum, the comparison of American and German radio production during this period underscores not only the technological supremacy of the United States but also reveals a broader, systemic industrial advantage rooted in automation, resource availability, and organizational efficiency. This chasm in capacity and technology went a long way in shaping the strategic landscape of the war, with American industries able to produce vast quantities of reliable equipment that continually outpaced German efforts to maintain parity, let alone dominance. By early 2014, meticulous calibration across the entire electromagnetic spectrum of radio frequencies had become a hallmark of American technological prowess. To put this into perspective, such precision in signal calibration required complex machinery, equipment that, at the time, could cost around $300 to produce. In stark contrast, the analogous German systems demanded entire laboratories, filled with a multitude of oscillators, attenuators, and frequency analyzers, which together ran up costs into the thousands of rich marks, all necessitating continuous calibration and maintenance by skilled engineers. This difference in complexity and cost was not merely a matter of expense but a reflection of the technological gap that was widening month by month. By the dawn of 1944, the message delivered to the Allied forces' technical intelligence units was both unambiguous and alarming. It was increasingly clear that American advantages in communications technology had become absolute, irreversible, and, importantly, were expanding at an alarming rate. Each passing month saw American factories producing more radio sets than the combined total of German military inventories. Every captured example of their equipment revealed subtle but significant improvements, embodying advanced design innovations and manufacturing sophistication that the Germans struggled to emulate. The accumulation of such evidence underscored the widening chasm in technological capabilities. The situation grew even more pronounced with the rapid deployment of American radar systems during late 1943 and early 1944. These systems transformed the battlefield by demonstrating the extraordinary possibilities when radio technology was pushed to its ultimate limits. Employing microwave frequencies and pulse techniques, American radar represented the peak of electronic development. The use of sophisticated signal processing, integrating rapid data analysis, precise tracking, and automatic adjustment, allowed for an unprecedented level of detection and targeting accuracy. These innovations facilitated the mass production of radar sets designed for a variety of military applications, including ships at sea, aircraft in the skies, and ground-based defense installations, all manufactured with the same industrial efficiency and scale as their voice radio counterparts. One significant example was the capture of an 584 Seychelles rupees fire control radar in March 1944, revealing capabilities that German radar scientists had only hypothesized about. This set operated at an extraordinarily high frequency of 3000 MHz, a range that necessitated specialized components and advanced engineering. It incorporated a precision tracking mount with automatic firing control circuits, enabling anti-aircraft guns to destroy enemy aircraft with remarkable accuracy and destructive power. The SCR508's weight exceeded 10,000 pounds, requiring a dedicated vehicle to transport and deploy it. Despite its size and complexity, American factories produced these radars by the hundreds, showcasing a level of industrial efficiency that Germans simply could not match. Meanwhile, German radar development remained largely confined to long wavelength systems operating below 1000 MHz. This focus was dictated by practical manufacturing limitations. German industry lacked the capability to produce the highly specialized vacuum tubes required for higher frequency operation. In particular, magnetron tubes used in American microwave radar demanded precise manufacturing processes, exotic materials, and advanced techniques that German industry did not possess. As a result, German engineers, despite their theoretical designs for microwave radar, faced insurmountable obstacles in translating these concepts into functional hardware, largely because the necessary components simply did not exist within their manufacturing capabilities. Throughout 1944, the systematic examination of captured American equipment continued apace as Allied forces advanced across the Italian peninsula and prepared for the invasion of France. Each newly captured piece added to the mounting body of evidence, underscoring the colossal technical superiority of the Americans. This included not only radar systems but also an array of radio communications equipment. Incremental improvements in radio design were regularly observed. For example, the 694 Seychelles rupees, introduced in mid-1944, provided tank units with radio communication capable of frequency modulation, offering increased operational range and enhanced reliability in challenging battlefield conditions. Further innovations included the 619 Seychelles rupees aircraft radio, which boasted hundreds of crystal-controlled channels and near-instantaneous frequency switching capabilities. These features allowed pilots and ground controllers to maintain continuous, secure, and adaptable lines of communication. Perhaps most critically, American equipment's reliability was steadily improving over time. Early models such as the 300 Seychelles rupees, produced before the latest advancements, occasionally suffered from issues such as moisture ingress or faulty battery contacts. However, captured samples from late 1944 revealed that these problems had led to significant redesigns. Cases were reinforced, seals were improved, and component modifications were implemented to ensure more dependable operation in the rigors of wartime use. In sum, the meticulous capture and analysis of American electronic systems throughout 1944 not only confirmed the enormous technological gap but also demonstrated the relentless pace of American innovation and manufacturing. Every advancement, whether in radios or radar, reinforced the reality that the technological battlefield was increasingly tilted in favor of the Allies, laying the groundwork for future operational successes built on cutting-edge electronic warfare capabilities. Throughout the course of the conflict, the technological arms race extended far beyond simple manufacturing. The United States invested heavily in not only developing radio equipment but also in ensuring continuous improvement of these devices, driven by insights gained from real-world battlefield experience. American engineers and military technicians constantly refined their communication systems, integrating feedback and lessons learned from the front lines into ongoing production lines. As a result, American radios became more reliable, more durable, and more suited for the rigors of combat. In stark contrast, the German military, which initially produced high-quality equipment, faced a steady degradation in quality as the war stretched on. The mounting pressures of the conflict, coupled with resource constraints and overextension, led to a decline in the craftsmanship and reliability of their radio systems. As materials grew scarcer and factories became overwhelmed by demands, the Germans were forced to replace superior components with inferior substitutes. The skilled workers essential for maintaining high standards were increasingly diverted from production lines to serve at the front in combat roles, further reducing the workforce capable of ensuring quality. This shift resulted in a noticeable decline in the manufacturing standards, leading to radios that were supposed to serve for many years beginning to fail within mere months of deployment. By the time the Allied forces initiated their Normandy invasion in June of 1944, German military intelligence had accumulated enough evidence to fully understand the extent of the Allied communication superiority. The Allied forces, when arriving in France, carried an overwhelming number of radios, more than the entire German army had in total. Each of these Allied units had secure radio contact with their battalion headquarters, and every battalion maintained a direct line of communication with the higher command levels, including division headquarters. This extensive network allowed artillery forward observers, situated dozens of kilometers away from their targets, to direct fire with unparalleled precision, all because their radios maintained steady, reliable contact. German commanders attempting to organize and coordinate their defenses, however, found their communication systems rapidly breaking down under the combined pressures of electromagnetic jamming, artillery bombardments, and the chaos intrinsic to wartime combat. The radios that had previously performed flawlessly on testing ranges proved to be unreliable in actual battlefield conditions. Hot summer temperatures in Normandy caused crystal oscillators within German radios to drift off their precise frequencies, making it impossible for units to maintain contact. Batteries powering these radios drained swiftly, yet supply chains failed to deliver replacements in the necessary quantities. The sophisticated German communication doctrine depended on a reliable network, but under combat stress, this ideal network simply disintegrated. The technical reports flooding back to Berlin grew increasingly desperate. Senior engineers and military officials recognized that the German electronic warfare effort was failing. By August of 1944, Sherman, one of the senior German engineers assigned to the weapons and communications operations, expressed the grim reality in his reports. Germany had already lost the electronic war. The Allied capabilities went far beyond just weak hardware. They included advanced jamming equipment, direction-finding systems, and comprehensive signals intelligence operations. These combined efforts enabled the Allies to quickly locate and target any German radio transmission within minutes. They broke German codes, monitored frequencies, and meticulously tracked movements through the analysis of intercepted radio traffic. The final blow came during late 1944 and early 1945, as Germany's industrial base was thoroughly compromised by relentless Allied bombing campaigns. Key German factories producing radios and related equipment were targeted and destroyed, rendering the production of new communication devices impossible. In November of 1944, the Telefunken facilities in Berlin, responsible for critical components, were annihilated. Similarly, Lorenz plants in Stuttgart were repeatedly bombed, disrupting ongoing production. The crystal manufacturing facilities located in Sudetenland fell into the hands of the advancing Soviet forces in January of the following year. By March of 1945, manufacturing of German radio equipment had effectively ceased. The few radios still operational at that stage were being maintained under increasingly dire conditions. Frontline technicians, faced with a lack of replacement parts, resorted to scavenging damaged sets for usable components and improvising repairs with whatever materials they could find in the field. Because no new radios were being produced, when a command headquarters radio failed, it meant the immediate loss of communication with entire units. The breakdown of these systems had dire consequences. Armored divisions and tank battalions, which relied heavily on radio communication for coordination, became isolated, vulnerable groups unable to respond effectively to battlefield developments. In this bleak reality, the once reliable German communication network was fundamentally broken under the weight of technological obsolescence, resource shortages, and relentless Allied pressure. The gap in communication capabilities was a decisive factor that contributed to the rapid collapse of German defense efforts in the face of the advancing Allies, underscoring how critical technological superiority and integrity are in modern warfare. On the battlefield, numerous issues arose from the inability of different vehicle units and soldiers to coordinate their actions effectively. These communication breakdowns often hampered strategic and tactical maneuvers, creating gaps that the enemy could exploit. Meanwhile, the United States, eager to maintain its technological edge, continued to refine and upgrade its military equipment even as the tide of victory was swiftly approaching. Among these advancements, new radio systems introduced in the early months of 1945 significantly enhanced operational capabilities. These radios boasted extended communication ranges, increased the number of available channels, and offered much greater reliability, minimizing the risk of signal loss during critical moments of combat. Despite the improvements, the high rate of production did not stem solely from a critical need for additional radios. Instead, it was driven by the industrial machinery's relentless push to keep manufacturing lines running at full capacity. The American factories operated around the clock, relentlessly churning out equipment with little regard for immediate necessity, simply because their manufacturing prowess allowed for such mass production. By May of that same year, American supply depots had become congested with radio equipment that, in many cases, would never see combat. The surplus was a testament to the scale of American industrial effort, which prioritized quantity and technological advancements over immediate distribution. The victorious conclusion to the European conflict arrived on May 8, 1945, when Nazi Germany capitulated unconditionally to the Allied forces. Among the items catalogued and collected by the occupying armies were important technical intelligence reports that had been gathered from German-occupied territories such as Tunisia, Sicily, and Italy. These documents, classified as highly secret by German authorities and concealed in salt mines as well as underground archives, offered the Allies a rare and comprehensive insight into the technological state of the German military machine. When American technical teams began examining German facilities in the summer of 1945, they were struck by the meticulous detail with which the Germans had studied captured American radios. The intelligence reports uncovered during these inspections proved to be remarkably precise, detailed, and professionally prepared. They correctly identified the technological advantages held by the Americans, while also honestly acknowledging the significant gaps in German capabilities. One particularly insightful report, authored by Oberingenieur Klaus Hermann in April of 1945 as Soviet forces advanced toward Berlin, served as a final testament to the Germans' recognition of their declining technological prospects. In his assessment, Hermann expressed the view that Germany's defeat had been inevitable the moment their engineers had first opened a captured American radio during their campaigns in Tunisia. The details, such as the frequency crystals, automatic circuits, and modular design, revealed an industrial philosophy that Germany could simply not replicate or match. The American approach had effectively industrialized warfare itself, applying principles of mass production to all facets of military technology. This allowed the United States not only to produce sophisticated equipment swiftly but also in staggering quantities. Hermann further concluded that the outcome of future conflicts would be determined less by the skill of soldiers or the brilliance of tactics and more by the capacity to sustain the production of advanced high-technology weaponry on a massive scale. While German soldiers were well trained, their generals competent, and their tactics generally sound, what Germany lacked was a sufficiently robust industrial infrastructure capable of supporting such technological production at the rate necessary to maintain parity. This deficiency was starkly illustrated even in something as seemingly simple as the production of radio crystals, which required precision manufacturing to tolerances often achieved by skilled teenage girls working in German factories. The fact that German laboratories struggled to produce only thousands of these components, compared to the millions manufactured by the Americans annually, highlighted the industrial gap. The post-war fate of many German engineers who examined captured American equipment echoed this reality. These experts found themselves in a changing world where industrial capacity largely determined military success. Klaus Hermann's work did not end with the war. He was recruited by American authorities in 1946 and devoted the next 2 years to meticulously documenting German radio technology for United States intelligence. His expertise proved invaluable, as he later became a consulting engineer for American electronics companies, helping them analyze and build upon the innovations that German engineers had developed, many of which were worth salvaging and improving. Many of Herman's colleagues and fellow engineers followed similar trajectories. The significant transfer of German technological knowledge and personnel to America, facilitated by programs like Operation Paperclip, represented a strategic brain drain from Germany. This movement of talent was instrumental in shaping the post-war technological landscape, fueling American advancements and ensuring that the United States maintained a decisive edge in electronic and military technology long after the war's end. During the tumultuous years of World War II, a significant influx of scientists and engineers from Germany found their way to the United States. These individuals brought with them a wealth of knowledge related to German technological advancements, but more critically, they absorbed and internalized the organizational principles and manufacturing methodologies that had contributed to America's eventual dominance in the war. Their expertise in engineering, combined with the innovative production techniques they adopted, played a crucial role in shaping the future of American industry. In the year 1952, a prominent engineer named Herman authored and published a comprehensive technical paper in the Proceedings of the Institute of Radio Engineers. The paper was titled, Comparative Analysis of German and American Military Radio Design Philosophy from 1939 to 1945, and it reflected years of meticulous research and wartime experience. Drawing upon detailed examinations of captured American radio equipment, an effort he had undertaken during the war, Herman documented in precise academic language the core differences in design philosophy between the two nations. This work, which built upon the insights he had previously conveyed to Germany's high command nearly a decade earlier, served as a foundational analysis. Herman's analysis made clear that American radio design prioritized several key principles: ease of manufacturing, operational simplicity, and unwavering reliability across diverse conditions. These priorities were considered more important than pushing the boundaries of technical complexity or maximizing the efficiency of individual components. In contrast, German engineers aimed for technical excellence, emphasizing sophisticated theoretical designs and economical use of components. They believed that highly skilled operators could offset any inherent limitations in their equipment through expertise and meticulous maintenance. The critical distinction lay in scale. The American approach was inherently scalable, designed to produce millions of units rapidly for worldwide deployment. This mass production mentality enabled the United States to equip its military and technological infrastructure efficiently and effectively. On the other hand, the German design philosophy, although technically refined, did not lend itself as easily to mass production and global distribution, limiting its overall impact on the war effort. Herman's paper soon became a staple in engineering curricula and military training programs across the United States. Its insights profoundly influenced generations of engineers who would go on to design technology for the Cold War era, the space race, and the burgeoning computer revolution. By analyzing the strengths and weaknesses of German design, American engineers gained critical lessons, understanding what worked in large-scale manufacturing and how organizational principles could shape technological dominance. These lessons contributed to America's sustained leadership in scientific and technological innovation, shaping its defense and industrial capabilities for decades afterward. By the 1980s, many surviving German engineers, who had played vital roles in technical intelligence during the war, gathered periodically for reunions and conferences dedicated to recounting their experiences. During these gatherings, they shared memories, exchanged detailed notes, and reflected on their wartime endeavors. One notable figure, Klaus Hermann, then in his early 70s, delivered presentations recounting his work on analyzing captured American radios in Tunisia and Italy. At a conference held in Munich in 1986, he displayed photographs of the very first 508 Seychelles rupees radios his team had examined in early February of 1943. The images he shared showed young German engineers meticulously inspecting the internals of an opened radio case, measuring circuits, cataloging components, and attempting to decipher unfamiliar technologies. Herman recalled to his audience that the moment they removed the first crystal holder and discovered 10 precise oscillators installed within a standard military tank radio, it became painfully clear that Germany was inevitably destined to lose the war. The frequency crystal, a tiny quartz wafer ground to exact specifications, symbolized the crossroads where physics, engineering, and industrial logistics intersected. Although in principle the crystal was not a complex device, any capable laboratory could produce one. Yet, manufacturing millions of high-quality, interchangeable crystals at a cost low enough to outfit every military radio was an entirely different challenge. Achieving such scale required an industrial infrastructure of unprecedented sophistication and capacity, an infrastructure that Germany lacked during the war. The backbone of this infrastructure was built in America between 1941 and 1945, and remarkably, it did not dissolve once the conflict ended. Instead, it expanded, matured, and laid the groundwork for a technological revolution. This infrastructure evolved into producing transistors, integrated circuits, microprocessors, and eventually the modern computers and communication systems that define the 21st century. The same American companies that had built this industrial backbone continued to innovate, pushing the boundaries of technology and laying the foundations for the digital world we inhabit today. That had been mass-produced. The radio crystals used in Sherman tanks eventually paved the way for groundbreaking technological advancements, including the development of semiconductors for space exploration, microchips powering personal computers, and the critical components that underpin global telecommunications networks. The insights gained by German engineers as they studied American equipment in Tunisia formed a pivotal part of the foundation upon which contemporary technology was built, influencing design philosophies and manufacturing processes for decades to come. These principles, designing equipment for ease of manufacture, standardizing components across different systems, and training operators to simply integrate testing into their routine, became central to the evolution of high-tech industries. American radio equipment used during World War II exemplified these innovations, embodying a way of working that prioritized scalable, reliable, and efficient production methods. The lessons learned from the war years solidified these strategies as the standard methodology not only in military manufacturing but across all sectors of advanced technology. The drive to produce in large quantities to meet soaring demand led to a focus on streamlined assembly, modular design, and quality control that could be seamlessly incorporated into mass production lines. In the year 1995, marking exactly 50 years since the war's conclusion, the Smithsonian Institution curated a notable exhibition titled Communications and Victory: The Radio War from 1939 to 1945. Among the many displays was an 508 Seychelles rupees tank radio, identified by its serial number, which coincidentally matched the unit examined by Obering Herman in Tunisia back in February of 1943. This radio, recovered from German archives and returned to the United States as part of a cultural and technological exchange program, served as a tangible link to that pivotal period. Adjacent to this relic, the exhibit showcased translated excerpts from German technical intelligence reports, providing insights into how German engineers observed, analyzed, and documented American radio technology. Visitors had the opportunity to read Herman's detailed observations regarding the quality of crystals, the intricacies of circuit design, and the levels of manufacturing sophistication. Photographs displayed engineers taking precise measurements of components, testing circuits with meticulous care, and recording data that demonstrated a keen understanding of American engineering prowess. The exhibition made it evident that German technical experts, though recognizing the dominance of American technology, did so with respect and clear understanding, accurately assessing its strengths and potential implications for the battlefield. To provide a comparative perspective, the show included German radio equipment alongside American models. For example, a FUG G5 tank radio was placed beside the American 508 Seychelles rupees, allowing visitors to perform direct visual comparisons. The German radio was noticeably larger and heavier, with a more complex operational interface, and it was ultimately inferior in every measurable aspect. Its engineering was excellent, constrained, however, by Germany's limited industrial capacity during the war. Conversely, the American radio reflected a philosophy of sufficient engineering excellence combined with the utilization of virtually unlimited industrial resources. It was engineered for reliability and ease of use in the field, even by operators with minimal training. The curator's narration underscored that the exhibition was not intended to glorify American technology or to unfairly criticize German equipment. Instead, it emphasized that both sides had skilled engineers capable of designing effective devices within their respective constraints. The underlying difference, the curator explained, was not rooted in intelligence, theoretical knowledge, or technical training but rather in the industrial philosophies and manufacturing capacities of the two nations. Americans prioritized systems that could be produced at scale and operated dependably in diverse conditions by personnel with basic training. Germans, on the other hand, designed systems optimized for expert operation, delivering superior performance when operated by highly trained specialists but lacking the ability to scale production efficiently for global wartime needs. The final exhibit element was a small transparent case holding a single, precisely cut quartz crystal, no larger than a postage stamp, that was recovered from the 508 Seychelles rupees examined in Tunisia. Encased in a hermetically sealed metal holder, the crystal exemplified the technological detail behind military radios. The accompanying label explained that this crystal, one of 10 installed in a standard American tank radio, was the result of roughly 40 hours of meticulous German effort, highlighting the intense level of precision involved in manufacturing these critical components. During the war, the United States produced an astonishing quantity of radio crystals, over 100 million units, to be exact. To put this figure into perspective, such an output would have required every German radio technician at the time to work tirelessly for 500 years straight. This staggering volume of production exemplified the industrial strength and technological prowess of America during that period. The exhibit showcasing these innovations drew in a crowd of more than 200,000 visitors over its entire year-long duration. Among the attendees were numerous veterans, many of whom had first-hand experience operating the very radio equipment now displayed, evoking a sense of nostalgia and pride. Additionally, the exhibit attracted engineers with a keen interest in the history of technology, eager to understand the evolution of wartime innovations. Some visitors were professional historians, focused on analyzing the industrial dimensions of warfare and how technological advancements impacted military strategies and outcomes. All of these visitors left with a richer, more profound comprehension of how a nation's industrial capacity is a decisive factor in determining the result of conflicts, shedding light on the often overlooked importance of manufacturing and technological infrastructure in wartime success. Klaus Hermann, a notable figure in this narrative, passed away in 1997 at the age of 84. His obituary, published in the magazine of the Institute of Electrical and Electronics Engineers, highlighted his significant contributions to radio technology, marking him as a prominent engineer of his time. The obituary also acknowledged his vital role in technical intelligence efforts during the Second World War, a period during which he provided critical insights into enemy capabilities. After the war, Hermann continued to influence the field by assisting American companies in understanding and assimilating German technological innovations. It was emphasized that he held a lifelong conviction that Germany's defeat was largely influenced not on the battlefield but within the confines of factories and production lines. He believed that victory and defeat in war were ultimately dictated by industrial strength rather than mere battlefield tactics or soldierly valor, and that the true battleground was the factory floor where production workers operated. His collection of documents, later donated to the Deutsches Museum in Munich, comprised over 2,000 pages of detailed technical reports, circuit diagrams, component specifications, and strategic evaluations penned between 1943 and 1945. These archives provided historians with invaluable insights into how German technical experts perceived American military technology and what intelligence they relayed to the Wehrmacht High Command. Among these documents, one of the most emotionally poignant was a personal letter Hermann wrote to his wife in April of 1945, as Berlin was falling to Soviet forces. Months earlier, he had sent his family to stay with relatives in Bavaria, but he remained in the capital city to perform final technical assessments until he received orders to evacuate. In this letter, he detailed his decision to destroy all classified documents and equipment to prevent capture by enemy forces. His reflections painted a vivid picture of his experiences examining American technology, from the earliest 508 Seychelles rupees radios in Tunisia to the latest radar systems captured in the Ardennes. Each example, Hermann noted, reinforced a singular conclusion. America did not merely possess superior equipment but adhered to a fundamentally different approach to warfare. He explained that Americans had industrialized every aspect of war, from radio crystals to entire armies, employing the same mass production philosophies that had transformed the manufacturing of automobiles and refrigerators. Conversely, Germany had attempted to fight an industrialized war using traditional craftsman methods. In Hermann's view, the disparity was not due to a deficiency in German technology or theoretical knowledge. In fact, in many fields, German engineers and scientists surpassed their American counterparts in understanding and innovation. Rather, he observed, theory alone does not win wars. Success ultimately hinges on production capacity. The nation capable of manufacturing more tanks, more aircraft, more radios, and every essential component in greater quantities will, in the long run, overpower any adversary, regardless of military skill or bravery. Hermann closed his letter with a sobering prediction that future conflicts would be even more reliant on industrial strength than previous ones. Victory, he believed, would belong to the nation with the greatest manufacturing capacity, the most cutting-edge technology, and the ability to produce precise components at high volume. This belief underscored the fundamental importance of industrial infrastructure and manufacturing excellence as the true keys to winning modern warfare. The beginning of a fundamental shift in warfare, one where technological supremacy alone no longer sufficed unless backed by unparalleled manufacturing capacity. That small, seemingly simple radio crystal, crafted with exacting precision from quartz, embodied a new era in military history. It signified a pivotal turning point when the outcome of conflicts increasingly depended not just on the skill and bravery of soldiers on the battlefield, but on the sheer scale, efficiency, and ingenuity of industrial production lines. The German technicians who meticulously analyzed American radio hardware during their campaigns in Tunisia, Sicily, and Italy grasped the profound implications of this evolution. They recognized that victory was no longer solely about technological sophistication or tactical brilliance, but had become inseparable from the ability to mass-produce essential components with uniform quality and at enormous volumes. This realization underscored the importance of establishing and maintaining a vast, organized industrial capacity capable of consistently delivering millions of identical units. The remarkable feat of American industry in producing an immense quantity of radio crystals, all adhering to the exact same specifications, had been unprecedented. Such a level of manufacturing precision and scale transformed the nature of modern warfare, shifting the battleground from the field of combat to the realm of factory production lines. It was an era where the true weapon was the industrial system itself, capable of turning raw materials into reliable, uniform hardware on an unparalleled scale. Furthermore, this evolution extended well beyond the production of military hardware like radio crystals. The core lessons learned during World War II in America's factories came to influence nearly every facet of both military and civilian manufacturing. The understanding that technological superiority was meaningless without the ability to produce it in large quantities, and that operational effectiveness depended heavily on reliable, mass-produced equipment, became fundamental principles guiding post-war industrial development. These lessons emphasized quality control, efficient design for manufacturing, the importance of training operators effectively, and the necessity of supporting complex systems throughout their operational life. The conflicts and experiences of the war thus laid the groundwork for what would become modern manufacturing paradigms. The American approach gradually evolved into a comprehensive philosophy: design with production in mind, focus on build-in quality, ensure personnel are well trained, support the equipment during its operational life, and scale production to meet demand. The innovations seen in American radio technology during the late 1930s and early 1940s exemplified this transformation. Today, these principles underpin global manufacturing practices across industries, emphasizing efficiency, consistency, and scalability that trace their origins back to those critical wartime lessons. Ultimately, the story that began with Obering engineer Klaus Hermann's inspection of a captured German radio in Tunisia in February of the year 1943 culminated in a profound upheaval of military and industrial strategy. The humble radio crystal came to symbolize the broader industrial revolution in warfare, a revolution in which victory was increasingly dictated not by battlefield tactics alone but by the capacity of nations to produce the vital components of modern military systems in uncontested quantities. The German engineers who scrutinized American equipment understood this shift as the dawn of a new era in warfare, one characterized by the dominance of economic and industrial strength over traditional combat skills. They saw that the future belonged to those who could outproduce and out-innovate their adversaries, turning factories into the true battleground in the ongoing quest for strategic supremacy. It was a momentous occurrence, an event that would resonate through the annals of history. The reports produced during that critical period did more than detail technical specifications. They signaled the end of one era of warfare and heralded the dawn of another. These meticulous documents captured not only the state of technological advancement but also foreshadowed a transformation in how conflicts would be fought in the future. The experts who observed, analyzed, and documented these developments understood that their insights pointed toward a new paradigm, a shift from traditional battlefield tactics to a war heavily reliant on industrial strength and technological dominance. Although their urgent warnings went unheeded by officials in Berlin, dismissed or overlooked, the precision and foresight embedded within their assessments remained undiminished. History has shown that the principles they identified during their analyses, such as the mass production of high-precision components, the automation of industrial processes, the standardization for easy interchangeability, and the intentional design for manufacturability, are foundational to every modern high-tech industry we see today. These concepts did not originate in the Cold War or the digital age but can be traced directly back to the insights gleaned from those early wartime efforts. For instance, the evolution from radiocrystals, which were ground in American factories during the year of 1943, to the complex microprocessors fabricated in Asian semiconductor plants in the 21st century is a direct link in an unbroken chain of technological progress. The underlying industrial philosophy that guided this progression has remained consistent over decades, with only the scale and scope expanding dramatically. Back in 1943, when German technicians examined captured American radio equipment in underground laboratories across occupied territories, they were not merely scrutinizing communication devices. They were peering into the future, a future where technology and industrial capacity would determine the outcome of conflicts. The detailed reports these engineers compiled, carefully classified, and diligently stored during the war became invaluable historical documents. These records did more than explain Germany's military defeat. They elucidated how the capacity of a nation's industry could decisively influence the result of modern warfare. Their conclusion, articulated in highly technical language but profoundly clear in its implication, was that Germany had attempted to challenge the most powerful industrial nation in the world without possessing the requisite manufacturing capacity. The tiny yet crucial radiocrystal, an oscillating device made of ground quartz and produced by young American women, epitomized the industrial advantage. The production methods used to create these small but essential components in vast quantities told the full story. In industrial warfare, quantity and quality of industrial output weigh heavily against tactical brilliance or individual heroism. Without sufficient industrial capacity, even the most brilliant strategies and innovative technologies could not guarantee victory. This fundamental lesson, learned by German engineers who carefully scrutinized American radio equipment during the dark days of occupied Europe, remains startlingly relevant today. In an era dominated by microelectronics, satellite communications, and computer-controlled systems, the core truth has not changed. The side capable of generating overwhelming quantities of high-technology equipment, through mass production and industrial prowess, will ultimately emerge victorious. During the years between 1941 and 1945, the Americans proved this principle in action, demonstrating how vital industrial capacity could be to winning a global conflict. The strategic and technological momentum gained during that period laid the foundation for the world we inhabit now. Since those tumultuous times, the global community has been continuously adapting to the profound implications of industrial strength, realizing that technological superiority alone is insufficient without the ability to produce at scale. The lessons learned then resonate even more powerfully today, underscoring that the true battleground is often measured not just on the front lines but in the factories and laboratories that sustain national power. The unwavering assertion remains that in modern warfare, victory ultimately belongs to those who can sustain a relentless, overwhelming industrial output, capable of manufacturing high-tech systems in quantities that their adversaries cannot match. The centuries-old truth, demonstrated vividly during World War II, continues to echo in the corridors of military and industry leaders as they navigate the complexities of 21st-century conflict.